everyone, welcome to IIT-JAM Chemistry tutorial number 48, and this is lecture number 7 of the physical chemistry chapter solid state, and the subtopic of this lecture number 7 is structure of diamond. First of all, let us calculate the edge length of the unit cell of diamond. You can easily calculate in the laboratory with the help of picnometer that what should be the volume of 12 gram of diamond. It has been found easily that the volume of 12 gram of diamond is 3.42 cc per 12 gram, that means per mole. So this is the molar volume of diamond. So this volume has been occupied by Avogadro number of atoms. Therefore, the average atomic volume should be obtained by dividing this number by Avogadro number. So the final result is 3.42 divided by 6.02 into 10 to the power 23 cc, and this is nothing but 5.674 into 10 to the minus 24 centimeter cube. This is the average atomic volume of the carbon atoms within diamond. Okay. So if the unit cell has n number of atoms inside the cell, so n number of atoms means if n is 1, then it is simple cubic or primitive. This n is 2, this is body centered cubic or C face centered cubic. If n is 4, this is face centered cubic. And if the number is more than that, then within the FCC lattice there are some additional number of atoms within the unit cell. So how n and a are related with each other? Volume of the unit cell, if edge length is a, then volume of the unit cell must be a cube. Then this is the volume of one atom and this is the number of atoms within the unit cell. So if it is 1, then this one into 1. If it is 4, then this one into 4, and so on. So we don't know which type of space lattice is being followed by diamond molecule. Okay, diamond molecule or lattice, whatever you say. Then in that case we can relate this by this equation: a cube equals to 5.674 into 10 to the minus 24. This is the average atomic volume into number of atoms within the unit cell. And finally, from this we can get the value of a by taking the cubic root of this parameter. So 5.674 into 10 to the minus 24 into n to the power 1/3, and centimeter cube, by taking the cubic root it becomes centimeter. So finally, if n equals to 1, then a equals to 5.674 into 10 to the minus 24 into 1 whole to the power 1/3 centimeter. This value is 1.784 into 10 to the minus 8 centimeter equals to 1.784 angstrom, because 10 to the minus 8 centimeter equals to 1 angstrom. This way, for n equals to 2, n equals to 4 and n equals to 8, these values are obtained. For n equals to 2, it has been obtained to be 2.248 angstrom. For n equals to 4, it has been 2.831 angstrom, and finally for n equals to 8, it has been found to be 3.568 angstrom. Now this is the XRD pattern of the diamond crystal. Now experimental observation from 100 plane shows that the space of this 100 plane, that means the distance of the two planes, 100 planes, is 0.885 angstrom. Therefore, from this you can calculate the value of a, because d is a divided by root over 1 squared, 0 squared plus 0 squared. Okay, so this is 1 by root over 1, that is a. So a is also equal to 0.885 angstrom. Therefore, if it is 0.8885 angstrom, then it must not be simple cubic, because the simple cubic value does not resemble with this. Now reflection from 111 plane. This is the signal for 111 plane. You can calculate this value. If this theta value, 2 theta value is 44, so theta is 22, and from this, by using n lambda equals to 2d sine theta, and this is copper K alpha line, so the wavelength of the X radiation is 1.54 angstrom. So we can easily calculate from there the value of d, that is the spacing between 111 planes. It has been found to be 2.05. You can do it yourself. So from this you can get the value of a also. What should be the value of a? Because we know that d111 equal to a divided by root over 1 squared plus 1 squared plus 1 squared. That means a by root 3. Therefore, a must be d into root 3. Okay, so a equals to d into root 3. So we know the value of d. It has been obtained 2.05 and into root 3 angstrom. So it is 3.55 angstrom. Now recall the table for different values. N equals to 1, 1.784. Okay, so this one was 0.885, so this is much less than 1.784. So the definitely it was not simple cubic. And here it matches with this one. 3.568 is close to 3.55. So it must be having 8 atoms within the unit cell. 8 atoms within the unit cell means it has face centered cubic 4 and 4 additional atoms within that face centered cubic lattice. So this corresponds to n equals to 8. This unit cell is face centered cubic, that means it has 4 atoms inside by default, and within this 4 additional atoms are present to make it an overall 4 plus 4 equals to 8 atoms within the unit cell. So this way we can now obtain that the diamond is following the face centered cubic lattice, and it has 4 additional atoms inside that unit cell. So suppose this is the unit cell. Okay, this is the face centered cubic unit cell. It has edge length A. Let us first divide this unit cell into 8 equal sized small cubes. This is the large cube, this is the main unit cell. Now you divide, just have a look here. We are dividing it into 8 small equal number of cubes. Equal sized cubes, not equal number, equal sized cubes. This is cube 1. This is top left front. Okay, this is front right top. This is front left bottom. This is front right bottom. Now this one, this is back right bottom. This is back top right. This is back top left. This is back bottom left. Okay, so this way 8 equally sized small cubes are obtained from here. Then place the carbon atoms in the 8 vertices and 6 face centers. So definitely this main cube has 8 vertices. So put 8 carbons, and it has 6 face centers also. This is one of the face centers. This is number 2, this is number 3, this is number 4, this is number 5, and this is number 6. So let's put this 14 number of carbon atoms within this on this pattern. Okay. After that, let us separate one small cube. Suppose this is the cube, front right bottom. This is the cube. We separate this. Okay, just take it out of this system. So this one has been separated. This one, you find that this small cube also has 8 vertices, but all the 8 vertices are not occupied. Look here, one atom. Okay, this atom is this atom. Here is no atom. This is that place. Here is one atom. This is that place. Here is no atom. This is the place. Now what about this one? This one is this one. This empty point is this one. This occupied point is this one, and this empty point is this one. So this front bottom right cube is taken here. So this one can have an atom in this position in the body center. Let us put this. Okay, this is the body center, and here we have already described each small cubes have had their corners alternately occupied by the carbon atoms. The corners are alternately occupied. So this one's occupation, no occupation, occupied, non-occupied, occupied, not occupied, occupied, not occupied. So all the corners or vertices are alternately occupied. Now if you put in middle this gray colored atom, then it takes the position of the body center of the small cube. Okay, so this way now you have to, out of the 8 small cubes, 4 alternate cubes have had their body centers occupied. Now you have 8 cubes here. So this way if you arrange them, then you have to put 8 atoms within their body centers of the small cubes. But you have 4 additional atoms. So how can you arrange them? You have to arrange them by alternate positioning. Suppose this one taking this place, then this one would be left empty. If you place body center here, then this one would be left empty. So how does it look? It looks like that. Okay, so instead of 8 body centers of the small cubes, you are occupying the 4 body centers alternately in the small cubes. Then each carbon atom is tetrahedrally bonded to 4 neighbors, resulting in a rigid. How it looks like this? So if this carbon is bonded directly to this ones. So this one should be bonded to this one should be bonded to this one should be bonded to this one, and as well as this one also. So this way 4 central carbon atoms should be bonded. How? It looks like this. Okay, I repeat here, it looks like this. Look, this is not directly bonded to any carbon. It is bonded to the small cube beyond this unit cell. Okay, there are attached unit cells also. So beyond this unit cell, this carbon is bonded. Therefore, each carbon atom has the same neighborhood relation to make it a symmetrically fashioned face-centered cubic lattice with 4 additional atoms. We take look of another picture, the same picture, but from another aspect it has been drawn. Okay, this is one of the body centers of the small cube. This is the second one, this is the third one, and this is the fourth one. Okay, this large cube is visible here. Okay, so if you are asked how many atoms are within this unit cell, then the answer should be 8. Okay, 8 are within the unit cells. 4 are occupying the body centers, then 1/8 into 8 in the corners, and then half into 6 in the face centers. So 8 into 1/8 is equal to 1, plus half into 1/3 equals to half into 6 equals to 3, making it 4. Then 4 body centers, 4 into 1, then 4 plus 4 equals to 8. And as it has been mentioned here, that symmetrically fashioned, that means the environment is symmetrical completely. Look at this. If you don't imagine this unit cell, then it is completely looking like this. This carbon is sp3 hybridized. These bonds are purely sigma bond, sp3 sigma bond. Okay, and all the carbons are making the chair conformation like cyclohexane. Look at the movement of this cursor. This is one of the chair conformers. Here also one of the chair conformations. Look at the movement of the cursor. This is one of the chairs. Here another chair. So you know the structure of cyclohexane. So it looks like cyclohexane. Okay, all the chair conformations of cyclohexane like structures are connected in an uniform way, so that the neighborhood relation are symmetrical. Okay, and here this is the small cube. This is the small cube. This small cube is now tilted. How? Look at this. This is the small cube. Out of the 8 cubes, this is the small cube. This one is this one. This one is this one. This one is this one. This one is this one, and this one is this one. So I hope it is clear to all of you. Now we have to calculate the carbon-carbon bond length, the sigma bond length, and the CCC bond angle from this information which has been obtained from the XRD data. Okay, so we have already found the distance edge length. Okay, it has been found to be 3.04. So we are going to calculate the bond length first. So from here to here, this distance. Okay, now if you start from here, then here this is the middle point of this small cube. That is, this is the center of gravity or the middle point of this small cube. Then if you extend this line, it will touch this point, this vertex. So actually from here to here, this is the body diagonal, and here to here this distance is half of the body diagonal of the small cube. So if you can calculate geometrically the half of the body diagonal of the small cube, then this is the bond length of carbon-carbon. Okay, so how we have calculated this? So edge length of the small cube is a by 2. Here to here, this is a by 2. Body diagonal of the small cube is definitely the edge length into root 3. So edge length is a by 2 into root 3. So this is the body diagonal of the small cube. Since the atom that occupies the center of the small cube, we are mentioning this atom here. Okay, this is at the center of the small cube. This cube is actually left front bottom cube. Okay, left front bottom cube. Okay, therefore the half body diagonal distance of the small cube is the CC bond length. So here to here, this distance is the carbon-carbon bond length, sigma bond length. Okay, sp3 bond length. Half body diagonal of the small cube. What is the value? It is definitely body diagonal divided by 2. Okay, so the body diagonal is a by 2 root 3. Okay, so the body diagonal is a by 2 root 3, and then if you divide this by 2, then you will get the half body diagonal, which is the bond length. So it is finally 3.55 into root 3 by 4 angstrom, and it is 1.54 angstrom. So this length is 1.54 angstrom, and from XRD data, with the help of XRD data and molar volume, we have calculated this. Okay, so this is very interesting thing, and this is nothing but the carbon-carbon bond length. Now let us calculate the carbon-carbon-carbon bond angle. Okay, if you are very good in geometry, then easily you can calculate this angle to be 108 degree 28 minutes. How? Look, this is the half of the body diagonal, this is the half of the face diagonal. Then sin theta value. Sin theta value means this one divided by this one. But take the sin inverse value. You will get, it will be found to be 54 degree 44 minutes. Then this angle is the double of 54.4 degree 44 minutes. Okay, so this way we have to calculate this. Let us calculate the face diagonal of the small cube. This is the small cube and this is the face diagonal. Face diagonal means edge root 2. The edge is a by 2. So edge into root 2, a by 2 into root 2. Okay, so this is a by 2 into root 2. We should have placed a bracket here. Okay, this root 2 actually is in the numerator, not in the denominator. Keep it in your mind, this root 2 is with a. Okay, so it is in the numerator, not in the denominator. Here this is, since we have placed the bracket, so it is automatically by default goes to the numerator, and this 2 is after oblique, this is in the denominator. Okay, so this is nothing but a by root 2. Okay, fine. A perpendicular is drawn from the central atom of the small cube to the face diagonal of the small cube. So here to here. Okay, this we are talking about this diagonal. This is the central atom, this is the face diagonal, and this is the perpendicular. If you draw this, then sin theta value. Okay, therefore sine of this value means this angle is CCC bond angle. So half of this bond angle, this angle. Okay, so half of this bond angle, and if you take the sine of this angle, then it is nothing but the ratio of this distance here to here, half of the face diagonal divided by half of the body diagonal. So this is nothing but sine half of the face diagonal, half of the body diagonal, both for the small cubes. And we know the value, half of the face diagonal of the small cube is a by 2 by root 2 divided by 2, because we have taken the half. Okay, then a by 2 root 3 divided by 2. Okay, a by 2 is the edge length. Okay, then edge length into root 2 is the face diagonal divided by 2, half of the face diagonal. A by 2 is the edge length, then edge into root 3 is the body diagonal, then divided by 2 means half of the body diagonal. Is it clear to you now? Okay, now this is nothing but sine root over 2 by 3, and the value is 0.8165. So the sine inverse of this value, okay, is nothing but this one. Okay, the bond angle divided by 2. Therefore, if you multiply 2 with this sine inverse value, then you will get the original bond angle. So carbon-carbon-carbon bond angle is 2 into sine inverse of 0.8165. The sine inverse of 0.8165 is 54 degree 44 minute, and the double of 54 degree 44 minutes means this is 88 minutes. 88 minutes means 60 minutes mean 1 degree, then left is 28 minutes, so 28 minutes. So 108 plus 1 degree, that was 109 degree 28 minutes. So the bond angle is also calculated from this XRD data. Keep it in your mind. How significant is XRD? Now the volume fraction. Okay, this is the small cube, and this is the central carbon atom, and 4 carbons in alternate corners of this small cube. Okay, this 2 has been drawn prominently, and left these 3 are drawn faintly, because these 3 are less important in calculating this thing here. So radius of one atom from here to here, this distance is r. Okay, now this is not actually a by 2 is not equal to 2r. Okay, this here to here, this distance is a by 2, because this is the half of the edge length, because this is the edge length of the small cube. Okay, this is not edge length of the large cube. Okay, so we have to relate a with r. How? Look, this point is the center of the body diagonal. So from here to here, 1r, here 2r. So half of the body diagonal is 2r. Okay. So half into body diagonal of the small cube equal to twice r. Therefore, twice r equals to half into, what is the value of body diagonal? Edge length into root 3. So edge length is a by 2, and then if you add multiply root 3 here, then you will get the length of the body diagonal, then half of the body diagonal is 2r. Therefore, from this we can get r equals to a root 3 by 8. Then volume of one atom means 4 by 3 pi r cube. Okay. So one atom 4 by 3 pi r cube means 4 by 3 pi into, instead of r we place this, we put this value a root 3 by 8, then whole cube. Then it gives the value pi a cube root 3 divided by 128. Now there are 8 number of atoms within the unit cell. Okay, we know that. Therefore, what is the occupied volume? The total number of atoms into volume of one atom equals to pi a cube root 3 by 16. Now what is the volume of the unit cell? This is the small cube. Then what is the volume of the large cube? Volume of the large cube is definitely a cube. Okay. Then the ratio of this one with this one is the occupied volume fraction. So occupied volume fraction is the occupied volume divided by the volume of the large cube. And this value is found to be 0.34. That means only 34% of diamond is occupied, okay, within the unit cell. Therefore, what should be the void space? The void space should be 66%. Now some important points. One carbon atom is surrounded by 4 nearest carbon atoms to which it is directly bonded by means of sigma bonding. Okay, sp3 orbitals are directly head-on overlapped in head-on fashion, and then these bonds are formed, and this, therefore the coordination number becomes 4. Now what is the second nearest neighbor? Number of second nearest neighbor is 12. So there are 12 more carbon atoms that are not directly bonded to the central one, but these are the second nearest neighbors. Thus the second layer coordination number should be what? It should be 12. The rigid three-dimensional network of diamond makes it the hardest known substance, and it gives rise to its high density and high melting point. The entire crystal of diamond is regarded as one large carbon molecule, and it is called a macromolecule. Now some other compounds or elements also have diamond type of structures. Let us see. The compounds or elements that have this similar type of structure are silicon, germanium, alpha-tin or gray-tin, zinc sulfide, mercuric sulfide, cuprous chloride, cuprous bromide. Now Ab2 type of structures are also found in this type of structure, fluoride, calcium, CaF2. Okay, and ice also has this type of structure. Let us have a look on this structure. Now you have 8 small cubes. If you fill one alternate cube, then you will get the Ab type of structure. But if you fill all the small cubes by fluoride ion, then you will get Ab2 type of structure, resulting in calcium fluoride. Therefore, an Ab2 type of compound such as calcium fluoride, CaF2, also follows the diamond type of structure. Here all the 8 small cubes are occupied by fluoride ions, and 8 vertices and 6 face centers of large cube are occupied by calcium cations. Thus each unit cell is comprised of 4 calcium fluoride molecules. Here one thing is important: zinc sulfide. This is zinc blend. Disturbing. This is zinc blend structure. Okay, so zinc blend structure is exactly similar to that of diamond. Okay, the diamond structure has been obtained from this structure actually. Okay, you have one question here. Look, the unit cell of diamond can be obtained from the unit cell of which one? Just we have discussed it is zinc blend. And what about sodium chloride, silver chloride? Look, sodium chloride, silver chloride are formed by interpenetration of 2 phase centers, one made by cations, another made by anions, anion means chloride. Cesium chloride is interpenetration of 2 simple cubic lattices, and it looks like a body centered cubic structure. Finally zinc sulfide. Okay, zinc forms the FCC lattice and sulfide occupies the alternate tetrahedral voids, that means small cubes, body center of the small cubes. So the answer should be option A, zinc sulfide. So that's all for this structure of diamond. Thank you and have a nice day.